Alright, y'all, so welcome back. We're going to continue where we left off last time with graphing trig functions. So last time we graphed the really simple ones in terms of the unit circle. Sine and cosine, the x-coordinate, the unit circle, and the y-coordinate. Today we're going to graph the other four. And what are they? Just remind me again.
Tangent, cotangent, secant, and cosecant.
Yes. Victoria, do you concur over there?
Yes.
Okay, great. It's tangent, cotangent, secant, and cosecant. Now, I know with the unit circle and with computations as well, these four trig functions, you usually think of them as being a little bit harder than sine and cosine to work with, yes? Well, actually, when it comes to graphing, they're actually a bit easier. And let me show you how. So, let's get a nice coordinate plane here. Let's go out, say a little bit more. And let's go 4 equal spaces. 1, 2, 3, 4. And for good measure, let's go 1 to the left as well. So let's first consider the graph of tangent. Tangent of x. Now, someone remind me, what is tangent as a fraction, as a quotient? It's always what divided by what?
Sine over cos.
Yes, sine over cos, the y-coordinate divided by the x-coordinate on the unit circle. So, I have a fraction with a variable in the denominator. Whenever you have that situation, so let's take the simplest case. If I say something like 1 over x, what immediately jumps out to you about stuff like this?
It's a fraction.
It's a fraction, but not just any fraction. We've got a variable in the denominator. It's not like, 1 over 3. That's kind of stale. There's nothing really too interesting about that.
It's a fraction that will have an undefined term.
Yeah, this thing is undefined at
0.
0, exactly. So when is tangent undefined? It's undefined when what equals 0?
Cosine of x equals
Yes.
0.
And when does that happen on the unit circle?
90 degrees.
Pi over 2.
Yeah, pi over 2, 90 is 1. What's another one?
3 pi over 2.
The other
3
one.
pi over 2. In other words, multiples of
Pi over
over
2.
2.
pi over 2, including negative ones as well. We can do clockwise and counterclockwise rotation. So notice, that makes the denominator 0, but let's say pi over 2. Does pi over 2 make the numerator 0?
No,
No.
that's
I
fine.
get 1 over 0. In other words, I have a non-zero quantity divided by 0. Right? Whenever that happens, what are you always going to have graphically?
An asymptote.
Yeah, what kind of asymptote?
Would it be vertical?
Yes, it would be vertical. Anytime you have non-zero divided by 0, that's a telltale sign, that's a giveaway for a vertical asymptote. So let's see here. Pi over 2, pi, 3 pi over 2, 2 pi, and negative pi over 2. We just decided that multiples of pi over 2 are going to make that denominator 0, but they're not going to make the numerator 0, so we're going to have vertical asymptotes. And multiples of pi over 2.
Multiples of pi over 2 that are exactly pi apart from each other.
Yes.
Right.
Okay.
Yeah, exactly pi apart. They have to be. So that brings us to another thing. These values in the middle of our asymptotes. You pick any two asymptote pairs, say this pair and this pair, take the value in the middle, and I've kind of given away by the picture already. What is a tangent of, let's say, 0? Sine of 0 over cosine 0?
That'd be 0.
Right. X-coordinate, y-coordinate divided by x is going to be 0 divided by 1, which is 0 right there. At pi, let me go ahead and put the unit circle on here. At pi radians, 180 degrees, I'm right there on the unit circle. What are the points for that, coordinates for that point?
-1 and 0.
Yes. And when I do sine over cos, y divided by the x-coordinate, in this case, I get
0 and negative 1, which is 0.
yes. So, tangent, as soon as you get your vertical asymptotes for a tangent graph, the middle x-coordinate's always going to have a y-coordinate of 0. Right in the middle, you always have a y-coordinate of 0. So the only question remains, how do I fill in the remaining portion? So let's just fixate ourselves on this one pair of asymptotes here, this region right here. How should I fill in? What was that?
Goes that like that and then like that.
How do you know that?
It's intuition.
Intuition. All right, well, let's put some details of that intuition, why don't we? Okay? So, pi over 2. If I get really close to pi over 2, but moving from 0, in other words, let's look at the action on the unit circle. 0 all the way to pi over 2. When I'm there, it's undefined, yes?
Right.
Sine over cosine 0. But let's say I get really, really, really close to it. Really, really close to the vertical axis, but not quite there. Let's say I'm at a point almost to pi over 2 rotations, counterclockwise. At this point here, is sine positive or negative?
Sine would be positive.
Yeah, I'm in the first quadrant on the unit circle. So sine's positive and
Cosine's positive.
positive. So a positive divided by positive is going to have to be
Up there.
up here. Yeah, so it's going to be somewhere here, and so we can connect it. I'll spoil this part for you. It goes like this. Like a little snaking action for the origin. Now likewise, if I do a clockwise rotation, if I go from 0 to negative pi over 2, because remember, on this horizontal axis we are plotting angle values, right? If I go from 0 to negative pi over 2, what that looks like on the unit circle is this. Now, of course, it's undefined at negative pi over 2. But if I get really, really close to negative pi over 2, from the right though, clockwise from the right, I land at a point that has a y-coordinate that's what?
Negative.
Right. Y is going to be negative, but x in quadrant 4 is...
Still positive.
Yeah, your x-coordinate is positive. So, sine over cos, y over x, negative over positive.
It's negative.
Negative, so I am down here. So, we get these nice snaking actions for the graph of tangent. So, there's one snake for this little segment, and I got another snake again, just repeats, for this segment, and so on and so on and so forth. The period of this guy is pi. From negative pi over 2 to pi over 2, it's half a circle, it's pi radians. And again. So, that is the graph of just plain old tangent of x. Any questions so far?
I noticed that the shape of tan of x looks very similar to y equals x cubed. Is there any relationship between the two?
No.
Not really?
No.
Okay.
It's a coincidence. But yeah, so let's see here. Now, just like we did for sine and cosine, once we got our parent functions, our prototype functions on the board, we started doing what to them?
Manipulate.
Yeah, we made life a little complicated for ourselves, and we vertically stretched, vertically compressed, horizontally stretched, horizontally compressed, reflected across the x-axis. So now let's consider the general case for tangent. More graphing. So again, your notes say, a tangent of bx plus c. I want you to change that to minus c, because that's what the book uses. And in case you do problems from the book, I want you to have that consistency. So, how are we going to graph stuff like this? Well, let's start with an example. How about y equals, not tangent of x. How about we change this guy 2 times tangent of x over 2. I want to go, hey, what does that graph look like? So you might think, it might have the same general sort of shape, right? The question is, how much does it stretch horizontally or compress horizontally? How much in the same considerations vertically? But now for tangent graphs that have these alterations, unlike the one for sine and cosine, there's actually a simple way to do these without having to do this in multiple stages. And that's to note the following. Tangent of this, whatever this quantity is, in this case it's x over 2, it could be 1,000,000 times x, whatever. In general, bx minus c. I know for a fact that whatever this is, at least one cycle, one repetition of my tangent graph has to be sandwiched between pi over 2 and what?
Negative pi over 2?
Yeah, remember the parent function graph for tangent. we had the typical repetition goes from negative pi over 2 to pi over 2. That's just the classic repetition that we look at when we think of sine. When we think of tangent. So, pi over 2, negative pi over 2. In this case, our stuff is x over 2. So someone tell me what you think I'm going to do next.
You can multiply the left and the right by 2 to just define the parameters for x.
Exactly. We know our parameters for x over 2. That's just using our parent function. But now when we multiply everything, like Jordan said, by 2, we get a nice inequality in terms of just x. So, I know at least one cycle has to be between these two things, negative pi and positive pi. Well, we also showed, using the parent function, that negative pi over 2 and pi over 2 were what geometric shapes? What kind of shapes in the coordinate plane?
They were the y-intercept.
Not y-intercepts, but what happened with the tangent graph at negative pi over 2 and pi over 2?
It goes to the top.
They were undefined.
It goes to the top, yeah, undefined. Mm-hmm. It's indicated by a vertical asymptote. Right. So, I know I have vertical asymptotes there and there. So let's put that here. Negative pi, positive pi, asymptote, asymptote. And voila, we have one repetition of our tangent function. Okay. And we know our tangent function is symmetric. It just repeats. So what can I do next? One repetition goes from negative pi to positive pi. Let's say, what's the next repetition up to the right look like?
Pi to 2 pi.
No, not pi to 2 pi.
3 pi.
Yes, these are spacings of 2 pi. So, just do one more for good measure. Dot, 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 dot. And so, there we go. Like so. Now, you may think, okay, we've done some stuff with x over 2, but where in the world does this 2 out front come in? How does that affect the basic shape of this graph? Well, what I want you to do next is, once you get this, I want you to locate the point right in the middle. Let's say you have one repetition here. The classic repetition, negative pi to positive pi here. Where does this graph cross the x-axis?
That's 0.
At 0, yes. And now here's where I want you to do something that you might not think of. What is the x-coordinate right in between? What's the midpoint on the x-axis between this vertical asymptote and the origin? And that x-intercept, in this case.
Pi over 2, right?
Yes. Right there. Well, negative pi over 2.
Oh, that's okay.
It's fine. I heard what you meant. Know what you said. Alright. What's the midpoint between this vertical asymptote and this x-intercept?
Plus pi over 2.
Yes. Plus pi over 2. Now here's the question. What is 2 times tangent of pi over 2 divided by 2? If you were to stick any one of these two midpoints, let's say this one or this one. Actually, let's start with negative pi over 2. If I were to stick negative pi over 2 in for x, what would I get as the value for this?
Be negative pi over 4.
Yes, 2 times tangent of negative pi over 4. Someone help me out. What is tangent of negative pi over 4? And we can use the unit circle.
Minus 1, right?
Yes. Negative pi over 4, clockwise rotation, gets me to a point unit circle of root 2 over 2 and negative root 2 over 2. So you divide them by those, you get negative 1. So negative 1 times 2 gives you?
Negative 2.
Yes, negative 2. And likewise, if I were to plug in this point, pi over 2 this time, I get 2 times tangent of pi over 2, which, someone help me out, comes out to be?
Positive 2.
Positive 2. In other words, these midpoint values between a vertical asymptote and an x-intercept is always going to have a corresponding y-coordinate this first one, let's see. I'll indicate it with an arrow. Negative pi over 2, negative a, where a is the leading coefficient in front of tangent.
Is there any definition for A? Is that called the amplitude in this case? Or
No, we don't think about it like that.
Okay.
But it's definitely a vertical stretching factor or compression factor.
Right.
So that's negative pi over 2 to negative a. Likewise here, if I were to go up, this point is going to be what? Pi over 2 comma
Positive A.
positive a. Again, a is this guy right here. So this is where this leading number comes into play. It has to do with these little midpoints in between the x-intercept and any given vertical asymptote. Does that make sense? All right, cool. So, any questions about that? All right, we can generalize this process of what we just did. So anytime you got something that looks like this and you want to graph it, what do you think the first thing I'm going to do is? What was the first thing I did for this graph to get it? I set up what kind of thing?
We set up the boundaries for the two vertical asymptotes.
Exactly. We set up an inequality. Set up some boundary. So, step 1. And again, this is to graph stuff like this. Is to simply take this quantity here, whatever's on the inside, bx minus c, and sandwich it between what two values?
Pi over 2 and negative pi over 2?
Yeah. Again, just look at our classic picture for tangent. Plain old tangent, the parent function. The classic repetition is negative pi over 2 to pi over 2. We know one cycle is trapped between here. So we take this, and then we solve for it in terms of x. We just want x in the middle. And that gives us our vertical asymptotes. And once we got our vertical asymptotes, what do? Just any pair of vertical asymptotes, then what do we do next for step 2?
Solve for A, I guess.
Not A. Well, before I found out my A, my midpoint's in purple here, what else did I need?
The reference point.
Yeah, and this the x-intercept.
The x-intercept, yeah.
The point in green.
Okay.
Point, reports, in green. You can choose any, whatever repetition you want, but I just chose that. So you want to find the x-intercept. For any given repetition. Okay, you just do that by taking your two values and doing what to them. Geometrically, what did I do? I looked at negative pi and pi, and I found the point that was
In the middle of
in the middle. I could have done it with this repetition, pi and 3 pi, and because all I have to do is just take these two values, add them together, and divide by 2. Exactly. So you basically were just finding the midpoint. And then step 3. Was to find these second midpoints in purple there. And we can think of these as the quarter points, for lack of a better phrase. When we find those quarter points, they always correspond to a y-coordinate that is, let's see. So the point of the 1/4 mark has a y-coordinate of what for tangent?
A and negative A.
The 1/4 mark. So if I was saying go from here to here, this is the 1/4 mark.
Right.
That's my x-coordinate. What y-coordinate does it have to have for tangent?
It would, that one's negative A, right?
Yes.
Yeah.
Negative A. At the 1/4 mark.
Okay. And the 3/4 mark would be positive A.
Precisely. your y-coordinate is positive a. So yeah, when you're graphing these, I want you, again, draw your repetitions, draw about 2 or 3 of them, but I want you to label these points for one repetition. In this case, pi over 2 and a. In this case, a is 2, and this is negative 2. So definitely draw this every time we graph a complicated tangent like this. Does that make sense? Mm-hmm. All right. Are there any questions about this before we move on to something else? Actually, before we move on, I want you guys to take a minute to try this problem. Just on your own. So use this procedure to graph y equals tangent of x minus pi over 2. This is the first problem on your worksheet for tangent. So go ahead and do that. Alright, so how do we do on this problem?
Pretty well.
Pretty well?
Yeah.
You in the corner, feel confident over there? You feel confident over there in the corner?
I think so.
Okay. Alright, let's find out. Let's find out how to title this. So if you guys notice, this has a very simple form. It has this plus or minus simple x and some quantity on to the right of it. Anytime you see that, you can always handle it if you want with just a simple horizontal shift. But because I want you guys to get more practice with this method, let's try it this way. But keep in mind, you could have done this just by a simple horizontal shift, pi over 2 units, in what direction?
To the back.
Yeah. But anyway, just get more practice with this, let's implement it. So all this stuff on the inside of my input, I'm going to take that and sandwich it between what and what.
Negative pi over 2 and positive pi over 2.
Yes. Negative pi over 2 and positive pi over 2. Alright, then you over there, what do we do next?
Solve for x.
Yes. By doing what to every single part of this tripartite inequality?
Add pi over 2.
Yes. Pi over 2 in the middle, and pi over 2 at the ends. And that gives us a nice inequality of x being sandwiched between what 2 values?
0 and pi?
Yes, 0 and pi. In other words, I know that one repetition is going to have what geometric quantities, what graphical quantities at 0 and pi?
Vertical asymptotes.
Yeah. Vertical asymptote there, and a vertical asymptote there. So, let's go ahead and graph those. Alright. Zoop, zoop. There's my 0. There's my pi. There's my asymptote. And again, because I know that the graph of tangent is symmetric, I can do what further from this?
You can find the midpoint between the two.
Pi over 2.
Pi over 2 is the x-axis.
Yes.
X-intercept.
X-intercept, yes.
Yes.
I've got an x-intercept pi over 2. And I also know that because the sign is, graph of tangent is nice and symmetric, this repetition over this distance is going to repeat left and right. So 0, pi, 2 pi, and we can stop there. Or we can do one more. Negative pi. Like so. Alright. So, there is my one repetition. X-intercept at pi over 2. What do I want to find next?
The quarter points?
Yes, the quarter points. The midpoints of these two line segments that I've created. So, one's right there. One's right there. Now look, for this one, I don't have to do any calculations. Based on the rule I just derived, I know that this coordinate here is a green, a darker green. I know that this coordinate here has to be what?
Negative pi over 4.
Pi over 4 and?
Negative 1.
And negative 1. Yeah. My leading coefficient is positive 1 right there. Whereas this guy, actually let's get our x-coordinates. That's pi over 4, then pi over 2. This x-coordinate, this quarter point is?
3 pi over 4.
Exactly, 3 pi over 4. So, 3 pi over 4 comma what?
Positive 1.
Yeah. Positive a, just a. Positive 1. And that's all you need to do, just graphing one period, one repetition. Alright, any questions about that? Good? Alright, let's look at the graph of cotangent. So someone remind me, what is cotangent as a fraction?
Cosine over sine.
Yes.
Or 1
Cotangent.
over 10.
But yeah, but in terms of two variable expressions. Two variable expressions, not just one. Cotangent as a quotient is cosine of the angle over sine of that same angle, yes?
Yeah.
So what do you want to do next? I want to figure out the graph of cotangent.
First find the vertical asymptotes and solve for when sine of x is 0.
Right. So sine of x is 0 when what happens?
When there's a vertical asymptote, right? Well, sine of x is 0 when x is
0.
0 or pi.
0, pi, anything else?
Multiples of pi.
2 pi, 3 pi, 4 pi.
4 pi, negative 2 pi, negative 3 pi, negative 4 pi,
Yeah.
yeah, left or right. So in other words, when x is any multiple of pi. Now, for multiples of pi, is my numerator, is cosine 0?
It's 1.
It's 1 or negative
1
1.
or negative 1, 1 or negative 1. In other words, a non-zero divided by 0 is a telltale sign of having what?
Vertical
Graphical.
asymptote.
Yes, vertical asymptotes. So, pi, 2 pi, 3 pi, and let's do one more, negative pi. The vertical asymptotes there, and a vertical asymptote there, a vertical asymptote there. Let's do another one right there. Am I forgetting anyone in this picture?
0, but that's already there.
Yeah, but I mean, you just don't indicate it. It's a very easy one to forget, so let's also indicate it. Let's use a green one. So, nice, evenly spaced vertical asymptotes. Now, just looking for tangent, what am I going to do next for cotangent? I want to find where it equals.
Wait, it's either positive or negative?
Well, not positive or negative, but once we got our vertical asymptotes, we want to find where the thing is.
Oh, 1. Like,
What about where it's 0?
but it's 0, okay.
So let's pick any repetition. Let's just pick this easy one. You got nice numbers, 0 and pi. Nothing too complicated going on numerically there. Where in this region is cotangent going to be 0?
Pi over 2.
Right, why do you say that? Because if I stick pi over 2 in there, I get cosine of pi over 2 over sine of pi over 2. What's cosine of pi over 2?
0.
0. Sine of pi over 2 is?
1.
So 0 over 1 is 0. So I got a nice point right in the middle. So again, it looks like we're going to have a symmetric graph. Right?
No.
Okay. Now, after we find that point, okay, we've got to analyze what is this thing doing around the vertical asymptotes. So, unit circle time. Going from 0 to pi. Okay? If I'm approaching pi, okay, I'm looking at this point here. If I'm approaching pi from the left, in other words, counterclockwise rotation. So, if there's a full rotation all the way to pi, I can't be at pi. But if I were to get really, really, really close to pi via counterclockwise rotation, i.e. moving towards pi from the left on the number line, I pick that point right there. What are the signs of the x and y coordinates at that point?
So the x would be negative and the y would be positive.
Yes. X is negative, y is positive. Positive divided by negative.
Is a negative.
Negative. So unlike the graph for tangent, so again, don't get this confused. For cotangent, when you move left to right, you're actually going down in your repetition. From there to there. Now let's see what I'm doing in this other segment, from 0 to pi over 2. If I'm approaching 0 from pi over 2, I'm approaching 0 from the right, i.e. I'm doing a clockwise rotation. Let's see here. I'm in which quadrant?
The first quadrant.
Yeah, I'm in the first quadrant. I'm some point over here. I'm just getting really, really close to 0 from pi over 2. Say that point right there. both x and y are positive, so x over y, y over x. No, y over x. No, x over y.
X over Y. Yeah.
Easy to get this stuff confused, guys. Positive or positive in this case.
Would be a positive.
Yes. So this thing is the flip, it seems, of the graph of tangent. Tangent, you know, your little snake was growing left to right in each repetition. Here's the exact opposite, and also, notice, we don't have asymptotes of pi over 2 and negative pi over 2. It's not multiples of pi over 2 anymore, it's multiples of
Pi.
Yes, exactly. So, we can go ahead and fill this out. Let's do one more. And so on and so forth, left to right. Now, I'm going to also give you guys some rules here for how to tackle a problem that gives you a more complicated graph of cotangent. So if you give A times cotangent of bx minus c plus d, you approach it in the same way. Let's say step 1 to graph. It's going to be to take, bx minus c, this quantity on the inside. But this time, what am I going to sandwich it in between? You can pick any interval you want, any nice repetition you want, but pick the nicest one, the one that's delineated by the nicest numbers.
0 and pi?
Yes. In this case, I'm not going to sandwich bx minus c by negative pi over 2 and pi over 2. I'm going to sandwich it between pi and negative pi. And then you solve for x.
Pi and negative pi? Or
You mean
pi and
0?
Oh, 0, yes, sorry. Oh, got that myself. 0 and pi. Then you solve for x. So, I'm not going to write the same words on the board. Solve for x. Step 2. Okay, just find the midpoint. It's going to be 0. The y-coordinate's going to be 0 there. It's going to be an x-intercept. Again, that's the same. And then the deal with step 3, you want to find the quarter points. Now, step 3 is almost the same as it was for the graph of tangent. But in this case, the x-coordinate at the 1/4 mark, let's say right here. Use it better. That guy's dead. So in this case, it's going to be pi over 4. 3 pi over 4. In this case, my y-coordinate's not going to be negative a at that quarter mark. Rather, it's going to be what?
Positive a.
Right, so it does a flip. It does a little reverse there. So y, unlike for tangent, is positive a. And then, what do you think the coordinate at the 3/4 mark is going to be? X-coordinate at the 3/4 mark yields a y-coordinate of?
Negative a?
Yes. Negative a. So guys, note the difference when you're solving these. For cotangent, you got 2 of them. First one is new parameters, new bounds, a new lower bound, new upper bound, and also different significances for the 1/4 and 3/4 marks respectively. Okay, so keep this in mind. But yeah, I think that's it for the graph of tangent and cotangent. Now I want you guys to try, hopefully this is a problem in your notes. Go ahead and give part C in your notes a good grapple. Okay guys, so a bit more of a complicated problem. We had some fair bit of action going on inside that input of that cotangent function, right? So what was it again?
Y equals -3 cotangent of pi over 2 times x.
Pi over 2 times x?
Yes.
X, so we got another nicest thing it looks like, right?
Mm-hmm.
So again, no matter what you have on the inside, you take that stuff and you sandwich it between some nice asymptotes for your parent function. So, what do you sandwich this guy between?
0 and pi.
Yeah, remember, this is cotangent, so it's not negative pi over 2 to pi over 2, it's 0 to pi. Now, to isolate x, what did I have to do to all 3 parts of this?
Multiply both sides by 2, and then divide by pi.
Yes. Multiply by 2 and divide by pi, or more simply, multiply by 2 over
Pi.
Exactly. So, what is 0 times 2 over pi?
Still 0.
Still 0. The thing in the middle just becomes
X.
x. And finally, you,
2.
the corner, pi times 2 over pi is plain old 2. So we got our vertical asymptotes. Or 2 of them anyway. But once we have vertical asymptotes, for tangent, for cotangent, and as we'll see later, for any trig function, we've automatically determined the spacing of our function. So I know I got asymptotes 0 and 2. And because all trig functions have nice symmetric graphs, this spacing repeats. 0 to 2, then 2 to 4, 4 to 6, and on forever, left and right. 0 to negative 2, like so. Okay, we just care about one repetition. Let's just pick a nice number, 0 to 2. We're going to point in the middle, our midpoint at 1. And someone tell me, how should I connect, well, not connect, but draw this repetition from this left asymptote to the right one?
Before taking negative 3 into account, or after taking negative 3 into account?
Okay, so let's first graph. So good catch. Just like you guys did in the last lesson, whenever you're dealing with a negative value out front, before we found the graph of the negative value times all that stuff, we first found the graph of what?
The positive value.
Yeah, the positive version. We just ignored the negative sign. So let's again this graph here. I'm gonna denote this in black. So y equals, let's graph this first. 3 times cotangent of pi x over 2. So in black here, what does this thing look like?
So it'd start from the top left and go down to the bottom right. Right.
Top left to bottom right in a nice snaking action. And this goes on forever. Let's do 2. Okay. Now, what's the next thing I want to find for this graph in black?
The quarter points.
Quarter points. In this case, quarter points happen where?
0.5 and 1.5.
Yeah, 0.5 or 1/2, and 1.5 or 3 over 2. So, I automatically know these 2 points. This one is 0.5 and what?
3.
Yes, our positive a value, the leading coefficient there. This one is 1.5 and negative 3. And this gives me a nice graph of 3 times cotangent of x pi over 2. Yes?
Yeah.
So final step, last step, is to do what to this guy?
To make it negative, which is just to flip it.
All right. So now in green, I want to graph y equals negative 3 times cotangent of all that stuff. I just take this guy, flip him over. I obtain precisely what I want.
That's a tan graph.
And it does look awfully like a tan graph. 0.5, and negative 3 this time, right?
Mm-hmm.
And 1.5, positive 3. All right. Any questions about that? You okay? Got a scowl on your face.
Yeah.
So you said it looks like a tan graph.
Yeah.
Is it basically the same as a tan graph?
Yeah, this is a tan graph.
Okay.
So
And I'll leave that as an exercise for you guys to figure out on your own. Which tan graph is this? But, yeah. So that is it, guys, for cotangent graphs and tangent graphs.